Hello everyone, I am Tanisha, a student of BSc Chemistry Honours first year. So today in this video, I will read chapter of DSC paper 1, Gaseous State. So let's start. Among the three states of matter, the gaseous state is the simplest one. Gases show maximum uniformity in their behavior irrespective of their nature. Gaseous state is characterized by the following physical properties. Gases possesses capacity of indefinite expansion. They acquire the volume and shape of the container. Gases are highly compressible. Unlike liquid and solids, gases can be liquefied at low temperature and high pressure. Gases have very low densities under normal conditions of temperature and pressure. Gases intermix spontaneously. This property is called as diffusion. Gases exert pressure on the wall of the container. Gases exert pressure equally in all the direction. The important measurable properties of gases are mass, volume, pressure, temperature, etc. The behavior of gases can be understood in the terms of relationship between these variables P, V, T and mass. These relationships are called gas laws. Gases which obey the gas law at all the temperature and pressure are ideal gases, while gases which don't obey these laws at all temperature and pressure are called non-ideal or real gases. Now, gases law. First is Boyle's law, pressure-volume relationship. This law describes the pressure-volume relationship of gases at constant temperature. It was given by Robert Boyle in 1662. This law states that at constant temperature, the volume of a given mass of a gas is inversely proportional to its pressure. For a given volume V of a gas at pressure P, Boyle's law may be expressed mathematically. V is inversely proportional to P at constant temperature, or PV is equal constant at constant temperature. Let V1 be the volume of a given mass of a gas at pressure P1 and temperature T. Now, if the pressure is changed to P2 at the same temperature, let the volume change to V2, then according to Boyle's law, P1 V1 is equal P2 V2, or P1 divided by V1 is equals to V2 divided by V1 at constant T. Thus, another statement of Boyle's law is the product of pressure and volume of a given mass of a gas at constant temperature is constant. Thus, if the pressure is half, the volume is doubled of its initial value, and if the pressure is double, the volume is halved. Now, Charles' law. Volume temperature relations. This law gives the relationship between volume and temperature of a gas at constant pressure for a fixed amount of gas. It was given in 1787 by a French chemist Jacques Charles and was further developed by Joseph Gay-Lussac in 1802. Charles law stated that at constant pressure, the volume of a given mass of a gas increases or decreases by 1 by 273 of its volume at 0 degrees Celsius for each 1 degree rise or fall in temperature. If V0 is the volume of a given mass of a gas at 0 degrees Celsius and V1 is the volume of a gas at 1 degree Celsius, then according to Charles' law, V1 is equals to V0 plus V0 divided by 273 is equals to V0 into 1 plus 1 by 273. If VT is the volume of a gas at T degrees Celsius, then Charles' law may be expressed mathematically. Vt is equals to V0 plus V0 divided by 273 into T is equals to V0 into 1 plus T divided by 273. Now, absolute scale of temperature. By similar calculation, it can be shown that the decrease of temperature results in the decrease in the volume of the gas. The volume of the gas below 0 degrees Celsius will be less than V0 and ultimately the volume should become 0 at minus 273 degrees Celsius. That is, at T is equal to minus 273 degrees Celsius, volume V is equals to V0 into 1 minus 273 divided by 273, that will be equals to 0. This is graphically shown in figure 1. Thus, minus 273 is the lowest possible temperature at which the gas is supposed to occupy 0 volume. That's the gas ceases to exist. This lowest temperature, minus 273 degrees Celsius, at which the gas ceases to exist is called absolute zero. A British scientist, Lord Kelvin, suggested a new scale of temperature based upon the choice of 0. This is called absolute scale of temperature or Kelvin scale, indicated by writing the letter K. Thus, minus 273 degrees Celsius or 0. The relationship between Kelvin scale and Celsius scale is Kelvin scale, Kelvin temperature is equal to Celsius temperature plus 273. T of K is equals to T degrees Celsius plus 273. With capital T is the temperature on Kelvin scale and small t is the temperature on Celsius scale. Celsius scale is converted into Kelvin scale by addition of 273. Alternative statement of Charles' law. Equation 1 can be written as Vt is equals to V0 into small t plus 273 divided by 273. Putting 273 plus small t is equal capital T in equation 2, we will get V at small t is equals to V0 into capital T divided by 273. Putting 273 is equal to we get Vt is equals to V naught into capital T divided by capital T naught, or V at small t divided by V naught is equals to capital T divided by capital T naught. V by T is equal constant at constant P. Here V is directly proportional to T at constant P. Thus Charles' law may be also stated as at constant pressure, the volume of the given mass of a gas is directly proportional to the absolute temperature. Let V1 be the volume of a certain mass of a gas at temperature T1 and pressure P. If the temperature is changed to T2, keeping pressure constant, the volume changes to V2. Then according to Charles' law, V1 divided by T1 is equals to V2 divided by T2 at constant pressure. Avogadro's law. V is directly proportional to N at constant T and P. This law relates the volume of a gas to the number of molecules at constant temperature and pressure. It was put forward by Amedeo Avogadro in 1811. Avogadro's law states equal volume of all the gases under similar condition of pressure and temperature and pressure contain equal number of molecules irrespective of the nature of the gas. It is known that 1 mole of any gas contains 6.023 into 10 to the power 23 molecule. Also that 1 mole of all gases are 273 and 1 atmospheric occupy a volume of 22.4 liters. This means that all as long as the temperature and pressure remain constant, the volume of the gas is directly proportional to the number of molecules. Mathematically, Avogadro's law may be expressed as V is directly proportional to capital N, T and P are constant. Further, the number of molecules N is directly proportional to the number of moles N. V is directly proportional to small n, where T and P are constant. Now, fourth is Graham's law of diffusion. Graham's law of diffusion states that the ratio of diffusion of a gas is inversely proportional to the square root of the density of the gas at constant pressure. Mathematically, R is directly proportional to 1 by under root D at constant pressure, where R is the rate of diffusion of the gas and D is the density. When two different gases are under consideration, then according to Graham's law, the rates of diffusion of gases are inversely proportional to the square root of their densities under similar condition of temperature and pressure. Mathematically, R1 divided by R2 is equals to under root D2 divided by D1. Further, as 2 into vapor density is equals to molecular mass, therefore we can write R1 divided by R2 is equals to under root M2 divided by M. If two gases diffuse under different pressures, say P1 and P2, then the rate of diffusion varies directly with pressure. In other words, greater the pressure, greater is the rate of diffusion. Hence, Graham's law can be written as R1 divided by R2 is equals to P1 divided by P2 under root D2 divided by D1 is equals to P1 divided by P2 under root M2 divided by M1. Now, Dalton's law of partial pressure. This law relates the pressure of the mixture of non-reacting gases contained in a vessel to their individual value. This law states at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressure which each gas would exert if pressure alone in same volume and at the same temperature. The individual pressure of the gas is known as the partial pressure. Mathematically, Dalton's law can be written as P is equals to P1 plus P2 up to Pn at constant temperature and volume, where P is the total pressure of the mixture of non-reacting gases and small p1, small p2 up to are the partial pressure of the gases. Now, ideal gas equation. The combination of Boyle's law, Charles law and Avogadro's law leads to an equation which relates the variable pressure, absolute temperature, volume and number of moles. This equation is formulated is called combined law gas law or gas equation. According to Boyle's law, V is inversely proportional to T at constant T. According to Charles' law, V is directly proportional to T at constant P. According to Avogadro's law, V is directly proportional to small n at constant T and P. Combining these three law of gases, we will get V is directly proportional to small n capital T divided by P and PV is directly proportional to NT and or PV is equals to nRT. Equation 4 is called ideal gas equation. In this gas equation, R is the constant of proportionality known as gas constant. It's independent of amount and nature of the gas. Nature of gas constant R. Ideal gas equation is equals to PV is equal to nRT or R is equals to PV divided by NT. It will be equal pressure into volume divided by mole into temperature at Kelvin. Since pressure is defined as force per unit area, hence R is equals to force per unit area into volume divided by moles into temperature. And we can write it force divided by length square into length cube divided by moles into temperature. But area is equals to length square and volume is equal to length cube. Then R is equals to force into length divided by moles into temperature K. Since force into length is equal work, therefore R is equals to work or energy divided by moles or temperature at Kelvin. Thus, R represents work done per degree per mole. The dimension of gas constant R as energy per mole per Kelvin. Since work is expressed in different units in different system, thus R has different numerical values. Numerical values of gas constant R, since R is equals to PV is divided by NT. Therefore, the numerical value of R depends on the units in which the pressure and volume are expressed. The numerical value of R is calculated for 1 mole of gas at NTP or STP condition where pressure and volume are expressed in different units. First, when pressure is expressed in atmosphere and volume in liters for 1 mole of a gas at NTP, the value of R is obtained in liter atmosphere per degree per mole, where P is equals to 1 atmosphere, V is equals to 22.4 liters, T is equal to 273 Kelvin, L is equals to 1 mole. Then, by using formula, R will be equals to 0.0821 liter atmospheric per Kelvin per mole. Second, when pressure is expressed in bar and volume in decimeter cube, 1 mole of any gas at 1 bar pressure and 273 Kelvin occupies a volume of 22.7 decimeter cube or 22.7 liter. Then, R will be equals to 0.0831 bar decimeter per Kelvin per mole. In SI units, pressure is expressed in pascals, P and volume in meter cube. Then, P R will be equals to 8.314 Pascal meter cube per Kelvin per mole or 8.314 Joule per Kelvin. In Celsius units, when pressure is expressed in per mole, dynes per square centimeter and volume in cubic centimeter, then R has the units Aux per degree per mole or calories per degree per mole for 1 mole of a gas at 10 Tp. We have P is equal to 760 mm or 76 centimeters is equal to 76 into 13.6 into 981 times centimeter per centimeter square. But after using this formula, R will be equals to 8.314 into 10 to the power 7 hours per Kelvin per mole. Further, we know 4.813 to 10 to the power 7 hours is equals to 1 calorie. So, R will be equals to 1.99 calorie per Kelvin per mole is equals to 2 calorie per Kelvin per mole. The value of R in different units has been given in the given table 1. Kinetic theory of gases. Kinetic theory of gases was the first theoretical attempt to explain the behavior of gases. The various gases were based on the experimental facts. There was no theoretical background to justify them. So, in order to account for the observed properties of gas, a model was proposed which takes into consideration the molecular nature as well as the kinetic nature of the gas. In 19th century, Maxwell, Boltzmann and Celsius put forward a theoretical model known as kinetic molecular theory of gases, which provided theoretical basis for various gas laws. The main postulate was to this theory are given below. Postulates of kinetic theory of gases. The main postulates of the theory are: first, all gases are made up of large number of extremely small particles called molecules. The molecules of a given gas are identical in size, shape and mass. Second, the molecules of the gas are separated from one another by such large spaces so that the actual volume occupied by the molecules is negligible as compared to the total volume of the gas. There are no attractive forces between the molecules of gas. They move completely independently. Now fourth, the molecules are in a state of ceaseless and random motion in all directions. During their motion, they collide with one another and also with the walls of the container. Fifth, the collision of the molecules with one another and with the walls of the container are perfectly elastic so that no energy is lost during collision. However, the energy may be distributed between molecules during collision. Now, sixth, the pressure of the gas is due to collisions of the gas molecules against the walls of the container. Seventh, due to collisions, the molecules possess different velocities and hence different kinetic energies. However, the average kinetic energy of the molecules is directly proportional to the absolute temperature. The motion of the molecules is unaffected by the force of gravitation. Now, kinetic gas equation. Kinetic gas equation is the mathematical expression derived from the postulates of kinetic theory of gases. This equation relates pressures and volumes of n molecules of a gas at given temperature to the root mean square velocity. Kinetic gas equation is derived as follows. Consider a certain amount of gas enclosed in a cubic box at a particular temperature. Suppose that the average length of the box is equals to L centimeter, number of gas molecules is equals to small n, mass of each volume of gas is equals to small m. According to kinetic theory of gases, the molecules are moving randomly in all directions with different velocities. Consider a molecule moving with velocity v centimeter per second in any direction. Velocity is a vector quantity and can be resolved into three mutually perpendicular components, Vx, Vy and Vz along x, y and z axis respectively. The component of velocities are related by the expression v square is equals to Vx square plus Vy square plus Vz square. Consider a molecule moving along x axis due to velocity Vx. the molecule will strike the opposite faces A and B. Momentum of all the molecules before striking face A is equals to mvx. As the molecules with face A is elastic, the molecule returns back to the same velocities but in opposite direction due to change in direction of the velocities taken as v minus vx. The momentum of molecule after striking face A is equals to m into minus vx is equals to minus mvx. The net change in momentum of the molecule is a single collision with face A is equals to mvx minus into minus mvx is will be equals to 2 mvx. Therefore, a molecule imparts a momentum of 2 mvx to the face A in one collision. Now, calculation of number of collisions per second on face A due to Vx component. For next collision on face A, the molecule has to travel from face A to B and then back from B to A. It has to travel a distance of L plus L will be equal to 2L centimeter. Since the velocity of the molecule is Vx centimeter per second, therefore distance traveled by the molecule in 1 second is equal to Vx centimeter. Since the molecule collides once on face A after traveling a distance of 12 centimeter, therefore the total number of collisions on face A in 1 second will be equals to Vx divided by 12. Change of momentum of molecules due to collision with face A in 1 second will be equals to momentum transferred in one collision into number of collisions per second. Will be equals to 2 mvx into Vx divided by 12 will be equals to mvx square divided by L. Similarly, change of momentum of molecule due to collisions with face B in 1 second will be equals to mvx square divided by L. Total change of momentum of molecule due to collision with faces A and B per second will be equals to mvx square divided by L plus mvx square divided by L plus is equal to equals to 2 mvx square divided by L. Similarly, change of momentum per second on two faces along y axis and z axis due to component Vy and Vz is 2 mv pi square divided by L and 2 mv z square divided by L respectively. Therefore, total change of momentum of one molecule per second on all the 6 faces of cube will be equal to 2 mv square divided by L. Similarly, the change of momentum on all 6 faces in 1 second for n molecules having velocities v1, v2 up to vn will be given as 2 ml into v1 v square plus v1 square up to vn square. And the total after calculation it will be equals to 2 mnu square divided by L, where u is the root mean square velocity and is expressed as u is equals to under root v1 square plus v1 square plus v2 square up to vn square divided by n. Therefore, the change of momentum per second is the rate of change of momentum, but according to Newton's second law, the rate of change of momentum is called the force. Thus, the force exerted by n molecules on 6 faces F is equals to 2 mnu square divided by L. By definition, pressure P is the force per unit area. P is equals to force divided by area is equals to 2 mnu square divided by L into 1 by 6L square will be equals to 1 by 3 mnu square divided by L cube will be equals to mnu square divided by 3v, where L cube is V, the volume of the cube, or PV is equals to 1 by 3 mnu square. This expression is called kinetic gas equation. Now, calculation of average transitional kinetic energy of gas molecules using kinetic gas equation. The average transitional kinetic energy of a molecule at a temperature T of the gas can be calculated. The average transition energy of a molecule is 1 by 2 mu square at temperature T. The total energy of the wall of the gas containing n molecules is kinetic energy equals to 1 by 2 mnu square. The kinetic gas equation is PV is equals to 1 by 3 mnu square will be equals to 2 by 3 into 1 by 2 mnu square will be equals to 2 by 3 K. This will be our equation 2. Comparing the equation with a general gas equation, PV is equals to nRT for 1 mole of gas, we will get RT is equals to 2 by 3 K or Ke is equals to 3 by 2 RT for 1 mole of a gas. The average kinetic energy per molecule can be obtained by dividing both sides of above equation by Avogadro's number n. Average kinetic energy for one molecule is equals to 3 by 2 RT divided by n naught is equals to 3 by 2 small k into capital T, where small k is equals to R divided by n naught and is called as a Boltzmann constant. Thus, kinetic energy is directly proportional to temperature. From this expression, it is clear that the transitional kinetic energy of an ideal gas is independent of the pressure, the molecular mass, or the nature of the gas. It depends only on absolute temperature T. Thus, at the same temperature, the average kinetic energy of hydrogen gas will be same as that of nitrogen. Kinetic energy and concept of absolute temperature. The kinetic energy for 1 mole of a gas is kinetic energy equals to 1 by 2 m n u square. Kinetic energy is directly proportional to u square. Further, from kinetic gas equation, we have derived that kinetic energy equals to 3 by 2 RT. This is equation 5th, or kinetic energy is directly proportional to T. This is equation 6th. Thus, kinetic energy of an ideal gas is directly proportional to absolute temperature T. From expression 4 and 6, we will get U square is directly proportional to T and U is directly proportional to under root T. Thus, the root mean square velocity of any gas is proportional to the square root of its absolute temperature. The molecular motion is therefore termed as the thermal motion of the molecules at absolute zero temperature. The kinetic energy is zero. In other words, the molecular motion ceases completely at absolute zero. It may be noted that absolute zero is the temperature at which molecular motion ceases completely. Now, deduction of gas law from kinetic gas equation. First, Boyle's law. This law states that at constant temperature, the volume of a given amount of a gas is inversely proportional to its pressure. Mathematically, it is expressed as V is directly proportional to 1 by P, or PV is equals to constant at constant temperature. Derivation of Boyle's law. Kinetic gas equation is PV is equals to 1 by 3 MNU square is equals to 2 by 3 into 1 by 2 MU square, where small n is equals to capital N, the total mass of the gas. Kinetic energy of the gas 1 by 2 MU square. Equation 2 can be written as PV is equals to 2 by 3 Ke. This is our equation 3. According to kinetic theory of gases, the average kinetic energy of molecule is directly proportional to absolute temperature. That's kinetic energy is directly proportional to T, or kinetic energy is equals to small k into capital T, where k is constant of proportionality. Thus, equation third can be written as PV is equals to 2 by 3 small k into T. This is equation 4. Right hand side of above equation is a constant quantity at constant temperature. Hence, PV is equals to constant at constant T. This is Boyle's law. Second, Charles law. This law states at constant pressure, the volume of a given mass of a gas is directly proportional to its absolute temperature. Mathematically, that's V is directly proportional to T at constant P, or V by T is equals to constant at constant P. As already derived in equation 4, we have PV is equals to 2 by 3 kT, or V by T is equals to 2 by 3 small k divided by P. This is equation 5. The term 2 by 3 small k divided by capital P is constant at constant pressure. This expression 5th is written as V by T is equal to constant. This is Charles law. Third, Avogadro's law. This law states that equal volume of all gases under similar condition of temperature and pressure contain equal number of molecules. Derivation of law. The kinetic gas equation for any two gases can be written as P1 V1 is equals to 1 by 3 MN M1 N1 U1 square. Kinetic gas equation for first gas. Equation number 6. And P2 V2 is equals to 1 by 3 M2 N2 U2 square. Kinetic gas equation for second gas. This is our equation 7. These equations can be expressed as P1 V1 is equals to 2 by 3 into 1 by 2 M1 N1 U1 square, or P2 V2 is equals to 2 by 3 into 1 by 2 M2 N2 U2 square. If both the gases are at same pressure, P1 is equals to P2. For equal volumes of both gases are taken, then V1 is equals to V2. Combining these two conditions, we can write P1 V1 is equals to P2 V2. This is our equation 8. This means left hand side of equation 6 and 7 are equal. Hence, 1 by 3 M1 N1 U1 square is equals to 1 by 3 M2 N2 U2 square, or M1 square M1 N1 U1 square is equals to M2 N2 U2 square. This is our equation number 9. From kinetic theory of gases, we know that average kinetic energy of a gas is directly proportional to absolute temperature. Since both the gases are at same temperature, therefore average kinetic energy of first gas will be equals to average kinetic energy of second gas. That's 1 by 2 M1 square is equals to 1 by 2 M2 U2 square, or M1 U1 square is equals to M2 U2 square. This is our equation 10. Dividing equation 9 by equation 10, we will get N1 is equals to N2. Hence, Avogadro's law is proved. Now, fourth, the ideal gas equation. For 1 mole of ideal gas, the gas equation is equals to PV is equals to RT. Kinetic gas equation is PV is equals to 1 by 3 MN1 square will be equals to 2 by 3 into 1 by 2 MNU square. Or PV is equals to 2 by 3 kinetic energy. Therefore, 1 by 2 MNU square is equals to kinetic energy. This is our equation 11. According to kinetic theory of gases, kinetic energy of molecules is proportional to its absolute temperature. Thus, kinetic energy is directly proportional to T, or kinetic energy is directly proportional to small k capital T. This equation 11 can be written as PV is equals to 2 by 3 small k capital T. This is our equation. The constant 2 by 3 k is equals to R, the gas constant. Therefore, equation 13 becomes PV is equals to RT, which is the ideal gas equation for 1 mole of ideal gas. Now, Graham's law of diffusion. This law states that under similar condition of temperature and pressure, the rates of diffusion of gases are inversely proportional to the square root of their densities. Mathematically, it is R1 by R2 is equals to under root D2 by D1, or R is directly proportional to 1 by under root D, where R is the rate of diffusion and D is the density of the gas. Kinetic gas equation is PV is equals to 1 by 3 m1 u square is equals to 1 by 3 capital M u square, where small m into small n is equals to capital M, therefore total mass of the gas. Or u square is equals to 3pv divided by m is equals to 3p divided by m divided by v is equals to 3p divided by d. Therefore, m divided by v is equals to d and is the density of the gas. Or u is equals to under root 3p divided by d. This is our equation 14. Thus, the rate of the diffusion of a gas is proportional to velocity u of the gas. Thus, the more the velocity of the molecules, greater is the rate of diffusion. U is directly proportional to small r. This is our equation 15. From equation 14 and 15, we can write R is directly proportional to under root 3p divided by d. At constant pressure, above equation reduced to R is directly proportional to under root 1 by d, which is Graham's law. Now, sixth is Dalton's law of partial pressure. This law states that at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressure which each gas would be exerted if pressure are on the same volume. Mathematically, P is equals to P1, P2 up to Pn, T and V are constant, where P is the total pressure of the mixture of gases at temperature T and volume V, and P1, P2 are the partial pressure of the gases. According to the kinetic gas equation, PV is equal to 1 by 3 mnu square, or P is equal to 1 by 3 mnu square divided by V. When first gas enclosed in a vessel of volume V, the pressure exerted by the gas is given as P1 is equal to 1 by 3 m1 n1 u1 square divided by V. When second gas is put separately in the same container of volume V, the pressure exerted by the gases P2 is equal to 1 by 3 m2 n2 u2 square divided by V. Now these gases are put together in a container having volume V, then the total pressure is given by P is equal to 1 by 3 m1 n1 u square divided by V plus 1 by 3 m2 n2 u2 square divided by V, or P is equal to P1 plus P2. Hence, Dalton's law is derived from kinetic gas equation. Now, ideal and non-ideal or real gases. A gas which obeys the general gas equation PV is equal to nRT and all other gases law at all temperatures and pressure is called an ideal gas or perfect gas. However, experiments show that the gas are obeyed fairly well as at low pressure and moderately high temperature, but the pressure is increased or the temperature is decreased. The deviation from ideal behavior is observed. In fact, no gas obeys gases law or ideal gas equation. PV is equal to nRT. Over the entire range of temperature and pressure, we can say no gas is perfectly ideal. The gases which don't obey the gas law and ideal gas equation at all the temperature and pressure are called non-ideal or real gases. In other words, a real gas is the one which obeys gas laws under the condition of low pressure and moderately high temperature. All gases are real gases and they show ideal behavior to different extent. Most of these show ideal behavior at low pressure and high temperatures. Amagat Andrews and other scientists made extensive study of behavior of various gases under different condition of temperature and pressure. They concluded that a real gas don't obey the ideal gas equation under all condition of temperature and pressure. It is observed that easily liquefiable gases like ammonia, carbon dioxide, sulfur dioxide, etc. show larger deviation from ideal behavior than gases such as hydrogen, nitrogen, oxygen, etc. Now, a comparison of ideal and non-ideal gas or real gas is given below. An ideal gas obeys gas law and ideal gas law equation at all temperature and pressure. A real gas obeys gas law only under similar pressure, under low pressure and moderately high temperatures. Ideal gas obeys ideal gas equation and non-ideal gases obey van der Waals equation, that's P plus AN square V square into V minus NB is equals to nRT. An ideal gas does not actually exist, it is hypothetical. All the gases which exist are real gases. Non-easily liquefiable gas like H2N2N2 O2 extra show nearly ideal behavior. Easily liquefiable gases like NH3SO2 CO2 extra show large deviation from ideal behavior. These are negligible intermolecular forces reduction in an ideal gases. The intermolecular forces of attraction appreciably, especially at low temperature or high pressure. The volume occupied by the molecules of an ideal gas is assumed to be negligible as compared to the total volume of the gases. A molecular volume is appreciable especially at low temperature and high pressures. Now, deviations from ideal behavior. An ideal gas obeys gas law or the ideal gas equation PV is equals to nRT under all condition of temperature and pressure. In fact, no gas is ideal. Almost all gases show deviation from ideal behavior. The real gas obeys gas law only under certain condition of temperature and pressures. The magnitude of deviation from the ideal behavior may be seen from the deviation from Boyle's law. According to Boyle's law, PV is equals to constant at constant temperature. Hence, for an ideal gas, the plot of PV versus P at constant temperature should give a straight line parallel to abscissa. However, we do not get a straight line. There is a significant deviation from ideal behavior. Plots of PV versus P for real gases are shown at 273 in figure 13. This type of curves are obtained. First, gases like S2 and helium obeys Boyle's law at very low pressure, but PV increases continuously as the pressure increases. Gases like CO, CO2 and CH4 show decrease in PV in the beginning, passes through a minimum which is different from different gases and then increase continuously with pressure. Now, measurement of deviation in terms of compressibility. In case of real gases, the deviation from ideal behavior can be measured in terms of compressibility factor is defined. Z is equals to PV divided by nRT is equals to PV into PV ideal. In case of an ideal gas, Z is equals to 1 and independent of temperature and pressure. For ideal gases, Z can't be equals to 1. It's either greater than 1 or less than 1. The extent of deviation from Z equals to 1 is a measure of non-ideality of the gas. For real gases, the compressibility factor varies the temperature and pressure. In the following articles, we will study separately the effect of temperature and pressure on the compressibility curves of real gases. First, effect of temperature on compressibility factor. Figure 14 shows the variation of compressibility factor with pressures for S2, N2, CO2 and CH4 at a constant temperature. It is clear from figure 14 is at low pressure for all the gases, compressibility factor is nearly equal to unity. This means at low pressure, the real gases exhibit show nearly ideal behavior. While at high pressure, Z is always greater than unity, which indicates that gases deviate from ideal behavior at high pressure from ideal gases derived from ideal behavior at high pressure. For gases like S2 and helium, the value of Z is always more than unity. The value shows a continuous increase in the pressure as the pressure is increased. For gases like N2, O2, CH4 and CO2, the value of Z first decreases, that Z is less than 1, passes through a minimum and increase on the pressure is increased. For carbon dioxide, the dip is large than nitrogen, indicated that CO2 is more compressible than nitrogen. From figure 14, it can be predicted that whether a gas can be liquefied or not. The gases which show sharp decrease in the value of Z are more compressible and hence can be easily liquefied. Therefore, CO2, N2, O2, CH4 are easily liquefiable gases. Whereas the gas for which Z is always greater than 1 are less compressible and hence cannot be easily liquefied. In example, for S2 and helium, the value of Z is always more than unity, hence these gases are easily liquefiable. Effect of temperature on compressibility factor, Boyle's temperature. For real gases, the compressibility factor Z varies with pressure. This can be understood by comparing the plots of compressibility versus pressures of nitrogen at different temperature, as shown in figure 15. Figure 15 shows the plot of compressibility factor versus pressures at different temperature. It is seen that the initial dip in the curve decreases as the temperature increases. This means that the deviation from the ideal behavior becomes less and less with increase in temperature. Ultimately, a temperature is reached when the dip in the curve is minimum and Z remains close to unity over an appreciable range of pressure. At this temperature, the gases behaves like an ideal gas for a particular range of pressure. Hence, Boyle's law is obeyed at this temperature. The temperature at which a real gas behaves like an ideal gas for an appreciable range of pressure is called Boyle's temperature. The Boyle's temperature for N2 is 323 Kelvin 50 degrees Celsius. At this temperature, the value of Z for N2 remains close to unity over a range of almost 100 atmosphere pressure. Above Boyle's law temperature, the value of Z for a gas is always greater than unity. That's a gas always shows a positive deviation. Now, causes of deviation from ideality. We have studied that the real gases show ideal behavior only at low pressure and moderately high temperature. These gases show deviation from ideal behavior at high pressure and low temperature. These results are not in accordance with the kinetic theory of gases, as these gas law and the ideal gas equation is derived from kinetic theory of gases, which is based upon some assumption. And the assumption made in the kinetic theory of must be modified in order to study the observed behavior of the gas. In order to explain the deviation from ideality, van der Waals pointed out to faulty assumption of kinetic theory of gases. These faulty assumptions are: the molecules are considered as point masses and the volume occupied by the gas molecules is negligible as compared to the total volume of the gas. The forces of attraction between the gas molecules are negligible and the molecules move independently. These two assumptions are valid only at low temperatures at low pressure and high temperatures. Under these conditions, the volume occupied by the gas lies negligible as compared to the total volume of the gas, but at high temperature or at low pressure but at high pressures and low temperature, the total volume of the gas decreases appreciably, where the volume occupied by the molecules remains the same because the molecules are incompressible. Therefore, the volume of the molecules cannot be neglected under these conditions. Under the condition of high pressure and low temperature, the total volume of the gas is quite small. Consequently, the distance between the molecules decreases and intramolecular forces of attraction becomes appreciable and can be. Van der Waals equation of state for real gases. The general gas equation PV is equals to nRT is applicable to ideal gases only. In order to get an equation applicable to real gases, the ideal gas equation was modified by Van der Waals by introducing two correction terms, one for the finite volume and the other for intermolecular forces of attraction and repulsion between the gas molecules. Correction due to volume correction. The volume occupied by the molecules is not negligible in comparison to the total volume. This means that the molecules are not free to move in the entire volume. Thus, the free volume available to the gas molecules is less than the observed volume. As a result, the ideal volume of a gas is smaller than the observed volume V. Hence, some correction term has to be subtracted from the observed volume to get the ideal volume. Let V be the actual volume occupied by 1 mole of the gas molecules. As the gas molecules are in constant motion, it has been found that the effective volume occupied by the gas molecules is 4 times the actual volume. Thus, effective volume is equals to 4V. The effective volume is represented as V. Then the volume correction term for 1 mole of gas will be equals to V. If V is the volume occupied by 1 mole of gas, then the volume available to the molecules for free movement is V corrected is equals to V minus V. For n moles of gases, the correction term is Nb, that the corrected volume is given as V corrected is equals to V minus Nb. The constant B is called the excluded volume or co-volume per mole of the gas. Its value depends upon the nature of the gas. It may be kept in mind that B is not equal to the actual volume of the molecules, but it's a measure of the effective size of gas molecule. The value of B, it has been calculated to be 4 times the actual volume of the molecules can be calculated by considering a bimolecular collision between two rigid spherical gas molecules with radius equals to r. The distance of closest approach of is 2r is equals to sigma, the collision diameter. Therefore, two molecules cannot approach each other more closely than distance sigma. In other words, the volume occupied by a sphere of radius 2r represents the excluded volume for the two molecules. Thus, the excluded volume per pair of gas molecules is equals to 4 by 3 pi into 2r cube is equals to 8 into 4 by 3 pi r cube. The excluded volume per molecule is equals to 1 by 2 into 8 into 4 by 3 pi r cube is equals to 4 into 4 by 3 pi r cube is equal to 4 into Vm, where Vm is equal to 4 by 3 pi r cube is the actual volume of the single molecule. Thus, the excluded volume for 1 mole of a gas B is equals to 4 Vm into capital N, or B is equals to 4 Vm in capital N for 1 mole of gas, where N is Avogadro's number. The constant B is called van der Waals constant. Now, second is correction due to intramolecular forces. Pressure correction. Pressure of the gas is due to the forces with which the gas molecule collide with the walls of the container. As there are some intramolecular forces of attraction exist between the molecules of real gases at low temperature and high pressure. Therefore, the molecules striking the walls experience an inward pull due to surrounding gas molecule as shown in figure 17. Considering a molecule in the middle of the container as shown in figure 17, the molecule experiences uniform attraction by the neighboring molecules. The attractive forces cancel out each other and there is no net pull exerts on such a molecule. On the other hand, when the molecule is going to strike the wall, it experiences a backward drag due to inward pull of the neighboring molecules as shown in the diagram. As a result, the molecule striking the wall with a lesser forces because of the inward pull. Therefore, the observed pressure. Consider a molecule in the middle of the container as shown in figure 17. The molecule experiences uniform attraction by the neighboring molecules. The attractive forces cancel out each other and there is no net pull exerted on such a molecules. On the other hand, when the molecules is going to strike the wall, it experiences a backward drag due to inward pull of the neighboring molecules as shown in the diagram. As a result, the molecule strikes the wall with a lesser force because of the inward pull. Therefore, the observed pressure P is less than the ideal pressure P I. Thus, in order to calculate ideal pressure Pi, some correction terms should be added to the observed pressure. Ideal pressure is equals to Pi is equals to capital P plus small p, where P is the correction term due to inward pull. This inward pull on the molecule is directly proportional to first the number of molecules per unit volume in the bulk of the gas. Second, the number of molecules striking the walls per unit area at any given time. Both these factors are proportional to the square of the number of molecules per unit volume, N by V, the square of the density of the gas. Hence, pressure correction P is directly proportional to N square divided by V square, or P is equals to AN square V square, where A is a constant which depends upon the nature of the gas and is called van der Waals constant. Thus, ideal pressure becomes Pi is equals to P plus A divided by V square for 1 mole of a gas. Pi is equals to P plus AN square divided by V square for N moles of gas. Substituting the value of ideal volume and ideal pressure in ideal gas equation, PV is equals to nRT, we will get P plus AN square V square into V minus NB is equals to nRT. This is van der Waals equation of state for N moles of gas. For 1 mole of a gas, it becomes P plus A divided by V square into V minus B is equals to RT. The constant A and B are called van der Waals. The critical phenomena. According to kinetic theory of gases, the gas molecules are constantly moving. Hence, the gas molecules possesses kinetic energy. Further, the average kinetic energy of the molecule is directly proportional to the absolute temperature. As the temperature decreases, the kinetic energy of the molecule also decreases. As a result, the molecules move closer to each other and the intermolecular forces of attraction increases. If the process of lowering the temperature is continued, the intermolecular forces of attraction increases so much that the gas converts into liquid, that the liquefaction takes place. At a given temperature, the gas can also be liquefied by increasing the pressure. The increase of pressure also brings the gas molecule closer to one another and ultimately the gas liquefies. Thus, all gases can be converted into liquid at sufficiently low temperature and high pressure. In the process of liquefaction, the effect of temperature is rather more important than that of pressure. All gases can be liquefied by lowering the temperature at atmospheric pressure, but is not possible to liquefy all the gases at room temperature by increasing the pressure. There is an interesting observation that a gas does not liquefy above certain characteristics temperature, however high may be the pressure. The temperature is called the critical temperature of the gas. The critical temperature Tc of a gas may be defined as the temperature above which it can't be liquefied, however the high pressure may be applied to it. The critical pressure Pc is the minimum pressure which is sufficient to liquefy the gas at the critical temperature. The critical volume Vc is the volume occupied by 1 mole of a gas at critical temperature and critical pressure. Tc, Pc and Vc are called critical constant of the gas. Table 4 gives the value of critical temperatures Tc, critical pressure Pc and critical volume Pc for some common gases, as you can see. Andrew's study on critical phenomena, isotherms of carbon dioxide. Andrew in 1869 studied the critical phenomena in detail. He measured the variation of volume of carbon dioxide with pressure at different temperatures. The result of Andrew's experiment are shown in the graphical form in the figure 20. In each of these graphs, the volume is plotted against pressure P. Pressure at a constant temperature. The plot of P versus V at constant temperature is called an isotherm. The PV isotherm of CO2 at different temperature are shown in figure 20. Isotherm at 13.1 degrees Celsius. The isotherm at 13.1 degrees Celsius consists by three parts. First, the curve AB is a PV curve for gaseous carbon dioxide. At point A gaseous CO2 exists at low pressure. As the pressure is increased, the volume decreases along curve AB. Thus, curve AB represents the compression of CO2 gas. At point B, the liquefaction starts and the volume decreases suddenly. Second, the horizontal portion BC. Along the horizontal part BC of the isotherm, the liquefaction continues while the pressure is held constant. At C, all the CO2 gas is converted into liquid. Third, the vertical curve CD. This part of the isotherm is in fact the PV curve of liquid carbon dioxide. The curve CD represents that there is a small change in a volume by increasing pressure. This is almost vertical since its liquid is not compressible. Thus, in the curve ABCD, along the portion AB, only gaseous CO2 exists. Along portion BC, the liquefaction of CO2 exists in equilibrium with its vapor form, whereas along CD, only liquid CO2 exists. Second, isotherm at 21.5 degrees Celsius. Isotherm EFGH at 21.5 degrees Celsius is similar to that at 31.1 degrees Celsius. The difference is that the horizontal portion Fg of the isotherm is shorter. As the temperature is raised, the horizontal portion of the isotherm becomes smaller and smaller until at 31.1 degrees Celsius, it reduces to a point L. Third isotherm at 31.1 degrees Celsius. In the isotherm KLM, the horizontal portion has become zero. The KL portion of the isotherm represents the PV curve of carbon dioxide at constant at point L. There is appearance of liquid carbon dioxide at the temp. At this point, the boundary between liquid and gas phase disappears, as the gas and the liquid have the same density and are indistinguishable. There is no indication of liquefaction above 31.1 degrees Celsius. The temperature above which a gas can't be liquefied is called critical temperature. The critical temperature of CO2 is 31.1 degrees Celsius. The point L represents CO2 in its critical state. The corresponding pressure is called the critical pressure. Beyond L, the isotherm becomes nearly parallel to the vertical axis and marks the boundary between the gaseous carbon dioxide on the right and the liquid carbon dioxide on the left. Now, principle of continuity of state. At the critical temperature, the gaseous carbon dioxide cannot be distinguished from liquid carbon dioxide, which indicates that the conversion of CO2 gas into liquid CO2 or vice versa is not a sharp or discontinuous process, but it's a continuous one. In figure 20, if the ends of the horizontal portions of isotherms are joined, a parabolic curve CGLFB represents by dotted line is obtained. The point L at the peak of the parabola represents the critical point 31.1 degrees Celsius. Within this parabolic curve, both liquid and gaseous stages coexist, but outside the curve CGLFB on the right side only gaseous state is present, while on the left side only liquid state is present. It can be shown that below the critical point, the gaseous state can be converted into liquid state without having more than one phase present at any time. In other words, the change from gaseous into a liquid state can be carried out without any sharp discontinuity. Consider the isotherm of carbon dioxide. At the isotherm at temperature 31.1 degrees Celsius, consider a certain volume of CO2 represented by a point A. At this point, CO2 is gaseous, keeping the volume constant of the gases. CO2 at point A is heated till its temperature rises and above critical temperature and pressure reaches to point B. During the isochoric process, the pressure rises to a long path AB. Now the pressure is kept constant and the gaseous CO2 is cooled so that the volume decreases from B to C. At point C, the intermolecular forces are large enough to cause condensation. Hence, at point C, liquid CO2 is obtained. At point A, carbon dioxide is entirely gaseous, but at point C, it's completely in liquid state. The change of state has occurred during compression along B to C, but now here along the path ABC, the two phases coexist. It's either gaseous or liquid state. In other words, the change of state from gaseous to liquid or vice versa is continuous. This is called continuity of state.